Rather than alkylation, acylation. So same idea as all of the other reactions. Same pour drawing of benzene. Take benzene. Now let's react it with this compound here. Actually, I'm going to flip it around. Rather than taking an alkyl group, let's take this what's known as an acyl group. Also AlCl3. Same pour drawing of benzene. And now we've added this group to the benzene ring. And so this now here is known as an acyl group. So the mechanism will be the same as what we've seen before, except for generating a strong electrophile. And now I guess I'll flip the ace. Notice this is an acid chloride or an acyl chloride, just like we saw with all those carboxylic acid derivatives. Chlorine is all of these lone pairs of electrons. Aluminum trichloride, probably doing something similar to what we've seen already. So let's have a Lewis acid-base reaction happen. So this all looks the same, slightly different on the left. Cl plus, Al minus. And now this is the one different step, is that we need to generate the strong electrophile. And what happens is it looks like we probably want to break maybe this carbon-chlorine bond to parallel some of the things that we've seen earlier. Why don't we have one of these lone pairs of electrons on this oxygen come in here and kick out the chloride to form an AlCl4. And this might look different at first, but it's a very important intermediate that we're going to see. It's just a regular arrow. We would end up having, I'm going to redraw this, putting the C here for the carbon, so it's a little easier to see. Carbon, we have a methyl group dangling down below, and now we have a triple bond here. So this oxygen, or the carbonyl group, gave up a lone pair of electrons to form a triple bond. So it still has a lone pair of electrons here, and now since it gave that lone pair up, it actually has a formal charge of +1. This looks highly unstable, perhaps, unlike things that we've seen before. However, what really helps its formation is this actually is resonance stabilized. We can draw a pair of electrons in that triple bond actually moving up back onto that oxygen. We'll just keep it like this to draw a resonance structure. But now we have a carbocation. So that positive charge is actually resonance stabilized. And this is known as the acylium ion. So that looks like our strong electrophile. So now let's just go back to the reactions that we've seen all along. Let's redraw benzene. Let's draw our acylium ion. I'll draw the oxygen formal charge. Doesn't matter which one. And let's have this act as our strong electrophile. I think that's the best benzene so far. Now, what we're going to end up doing is forming a new bond between, we're using this carbon here, could be any one of them. New bond to the carbon. Carbon-oxygen double bond. CH3. Left with a formal charge. Here we can draw a resonance structure, so far a rhenium ion here. Now to regenerate our final product, we still have that AlCl4. Doesn't matter which chlorine we use. This one's close. Form our major product of interest. We'll keep the C there, we don't have to draw it. Plus again HCl plus AlCl3. So this is very useful because now we've generated the species that has a ketone. And now we can connect this back all the way to all that other ketone carbonyl chemistry that we've seen before. The other key point here is that because we're forming this acylium ion overall in the reaction here, there's no rearrangement. We're not forming a carbocation species. Instead, it's this psyllium ion. So in response to Angela's question, does it matter which resonance form of the psyllium ion is attacked? No. So you can draw it either way. I just drew it to the one that was on the left here, but you could use this resonance structure, have the benzene ring as attack here. So great question. Either one is fine. Whichever one is your favorite resonance structure. I'm not sure if this is my favorite one, but it just happened to be the one I drew. Okay, so I know we've been going here at a sprint for the last almost an hour. I'm going to scroll back up just a little bit. 5 reactions here. Notice the similarities. All of them are generating a strong electrophile. Not sure which one to point at. But there's a psyllium ion on the bottom here. Form our rhenium ion, and then have a deprotonation to generate the final product. And here we'll scroll back up. So we can add a halogen here at the very top, like we did last time. A nitro group, number 2. SO3H, sulfonation here in this reversible reaction. And then 2 reactions to add either an alkyl group or an acyl group. So Friedel-Crafts alkylation and acylation. And we don't want to be too down on this alkylation. It's just that here you're forming a carbon-carbon bond, which is very useful. However, there are limitations because it's subject to rearrangements. And so that's important for synthesis. We'll mention here, probably not until tomorrow, this acylation reaction, go to the last one here, is, actually, I can bring it up right now. Remember, we already know there's ways to get rid of a carbonyl group here. Right, so I said we'll take a break, but remember back to the Clemmensen reduction or Wolff-Kishner reduction, or even making a thioacetal and raining nickel. So there are ways that we can introduce the acyl group and then get rid of this carbonyl group. So back to Avas's question earlier, that was the yes or no part of it, is that a lot of times one can introduce an acyl group first because it doesn't have rearrangements, and then you get rid of the carbonyl group using the reactions that we've discussed. So why don't we stop for 5 minutes,